This is CPM Calculus, Chapter 3, number 149. So first we're asked to review problem Chapter 3, number 109. Okay. Then we're supposed to look on graph paper and graph the functions below and label their parts with increasing, decreasing, concave up, concave down, and point of inflection. Okay, then we're going to use the first and second derivatives to find the intervals of increasing, decreasing, and concavity, up and down. And then use different colors to represent the concavity. Okay, so let's go ahead and first review problem from Chapter 3, number 109. That one basically said that curves can be labeled with descriptors, such as concave down and increasing. So on graph paper, graph these here and label their respective parts. Use different colors to represent concavity. Alright, so here are the graphs. Okay, you can use a calculator to do this to help you find the graphs, or you can graph them by hand by plugging in points. Alright, so first let's go ahead and label these, okay, with descriptors such as concave down and concave up. So here in part A, this graph is all concave up, right? It's just a parabola facing upwards, so all concave up. Well, we could say that basically, let's write it below. Concavity right? We know that it's concave up from everywhere, so negative infinity to positive infinity. All right. What else do we know? So I could even, well, that's already drawn, right? It's all concave up. So where is it increasing? Well, let's go ahead and look at increasing and decreasing in different colors. So let's start with decreasing. Right, so decreasing from left to right, we're just looking at a function and we're going down, down, down here in green, right? Going down till we hit the vertex, so that's decreasing, right? And then let's choose I guess pink, and now we're going to be increasing, right? Now we're going up, 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 up. All right, so pink is increasing. All right, so this point right here, when x, we don't know exactly what it is yet, but x is around, I don't know, negative 0.5 or so, right? The x value here is where it goes from concave, not concave, from decreasing to increasing, right? Alright, so let's go ahead and look at part B. Part B is this graph, right? So let's look at concavity first, right? And so let's go ahead and look at concave up and concave down. Alright, so it's concave up. Well, we can see that it's curving down there, but here, right, I'm going to put in like this bright green, it's concave up, right? That's concave up. And in concave down, I'm going to use yellow. We have this part, it's concave down here in yellow. Concave down. It's hard to read the yellow, but just bear with it. It's concave down. Now, increasing and decreasing, let's do decreasing in dark green. Okay, so we're increasing from negative infinity till this point, then we start to decrease, 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 right? This is decreasing. And increasing, let's do in blue. Okay, let me scroll this down a little bit. So blue, here we are, we're starting from negative infinity up until we get to this point around x is negative 1 point something or negative 2. And then it starts to decrease, we already did, and now it increases again at this point, right? Alright, so that's kind of basically what we did in problem 109. So let's go back to this problem, right? So we reviewed that. And now let's go ahead and graph these functions below. Okay, here are the functions. So again, you can use your calculator or whatnot to help you. right? So let's go ahead and graph these. So this right here, the graph goes a little below, right, -10 on the y values. This one, it goes way above 10. So each ticker, each little square is 5. So it goes 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. Okay? So just be aware of that. So let's go ahead and label their parts with increasing, decreasing, concave up, concave down, and point of inflection. All right. So let's start here. Let's do both of these at, like, let's just look at increasing. Okay, so let's do increasing in orange and increasing in orange here. Okay, so here in f of x, we start increasing here at the vertex, right? Oh, it's not letting me draw that. Let me go ahead and, there we go. Right, here is where we're increasing, right? And here, this is increasing because we always look from left to right. So it's increasing till here, starts to decrease, and then it increases again from here to here, right? So increasing. Let's look at, let me just check these off. Increasing, now let's go and look at decreasing regions. Decreasing I'll do in blue. Let's do both of these. Okay, so here from left to right, we're decreasing, we're going down, 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 down until we hit the vertex. Here we have just this region right here where we're decreasing and hit the vertex here. Okay, so we did decreasing, now let's do concave up. Let's do that in this color. Concave up, in pink. Alright, so looking at our graph here, this one is all concave up, right? Now, I don't want to get rid of the blue, so I'm going to make this kind of thicker. It's just all concave up, right? The whole thing. Negative infinity to infinity. This one, we just have concave up. Well, it starts off as concave down. Then around here, it becomes concave up again, right? So there's that region. Now let's go ahead and look at concave down. And in this one, it's all concave up. So we have nothing, right? We could even say nothing like this. All right. And concave down here, we are going concave down from the beginning until we hit this point, right? So there's concave down in green. In pink, we have up. So that gives us, finally, we did concave down and up. And point of inflection is where the concavity changes, right? So this one, no inflection point, right? No inflection point or points. Here, this one has one right here where the concavity changes. One inflection point. All right. So that's just looking at the graph. That's doing all these things looking at the graph. So now let's go ahead and let's look at the first and second derivative, right? It says right here, look at the first and second derivative to find the intervals of increasing, decreasing, concave up and down, and so on. So let's go ahead and let me use this color. And so what is f prime of x? Well, that's the first derivative, right? And that's equal to, using the power rule, it's 2x plus 5, right? What's g prime of x? Again, using the power rule, we bring the 3 down. That cancels with the 1/3. It's just x squared plus 6x minus 1, right? The 5 becomes 0. All right, so that's the first derivative. Now let's also do the second derivative. Okay, so the second derivative I'm going to do in green, f double prime of x. Well, we just are taking the derivative of the first, and so that's 2, right? And g prime of x is derivative of the first derivative. which is 2x plus 6. Okay? So how do these, the first and second derivatives, help us define increasing, decreasing, and concavity? Well, let's go ahead and look at these. So let's draw the graph. Okay, so in red here, I'm going to draw the graph of f prime of x. Okay, so it hits my my y-intercept at 5, right? And basically it's 2 over 1 is the slope, so up 2 over 1, up 2 over 1, and so on, like this, right? So this is the graph of f prime of x, right? It kind of got sloppy down here, but you can see basically, right? This is the graph of f prime of x. And as you can see, where this f prime of x is negative below the x-axis, we see what? Well, we see it's decreasing, right? And f prime of x, where it's positive, our f of x is increasing. And where's the point of where our vertex is? Well, it's where this hits the x-axis, right? So let's go ahead and find those regions, right? So let's go ahead and use this and set it equal to 0. F prime of x equals to 0. And so that means 2x plus 5 equals to 0. So then let's just solve for x, minus 5 from both sides. 2x is equal to negative 5. Solve for x, divide by 2. X is equal to negative 5 over 2. Okay? So this point right here is negative 5 over 2, right, where it hits the x-axis. Well, negative 5 over 2 is also the x value for the vertex. So negative 5 over 2, comma, some y value. We can plug in negative 5 over 2 into this to get the y value. So let's go ahead and do that. Let me bring up my calculator. I have negative 5 over 2. Oops. Negative 5 over 2. Whoa, what am I doing? Let me start all over. Open parentheses. No. Oh, I think I'm pushing shift. There we go. Negative 5 over 2 squared plus 5 times negative 5 over 2 plus 5 times negative 5 over 2 minus 6. Okay, that's going to give me the y value of negative 49 over 4, or what that is approximately is negative 12.25. So that point right there is here. Okay, so now we can use that information to say exactly where it's increasing or decreasing, right? So let's put away the calculator, and I can say, well, given that point, everywhere to the left up until that point, I can say it's decreasing, right? Because it's negative there. So I can say decreasing, and I can actually put in specific regions, right? I can say from negative infinity to this x value, negative 5 over 2. So negative infinity to negative 5 over 2, right? That's the region where the graph is decreasing. Increasing, right? I can use this to know, well, it's increasing starting at negative 5 over 2 to positive infinity, right? Negative 5 over 2 to positive infinity. All right, this is using the algebraic of solving for when f prime of x is equal to 0, right? So that's what we did so far. So concavity now, well, let's go ahead and look at f double prime of x, and that's equal to 2. So let's graph this, right? So this is f double prime of x here in green, and it's positive, right? Positive. It's constant. It's just a positive constant line, horizontal, right? Well, the fact that it's positive everywhere is telling us that the concavity is going up. All right. So just this positive is telling us concavity from negative infinity to infinity is up. All right. And nowhere is it down. Okay. And also because this does not cross the x-axis, no point of inflection. All right. So let's look at it into a little more deeper in part B with g of x. So let's start off by graphing. Let's use our calculator just to help us out. To graph the parabola x squared plus 6x minus 1. Okay, so go ahead and graph this. X squared plus 6x minus 1. Alright, so graph this. Okay, I need to zoom standard because I don't see anything. So zoom standard is going to put the x-axis here. Right? So there's my parabola. If I trace it, it's going to help me figure out kind of where I'm hitting some key points, right? At x is 0, I know that y is going to be negative 1, and my vertex is close to here at negative 3.5-ish, yeah? Yeah. Let me see. Actually, it's closer to negative 3. Yeah. Okay? So let's take red. I'm going to graph g prime of x. And remember, these are all 5 increments. So negative 3, comma negative 10 is going to be like right around here. And it's going to go up here. Right? So this is g prime of x. Alright? That's in red here. And what does that tell us? Well, let's go to the calculator. And remember where over here when we did this one, where it hit the x-axis, right? That's where we changed from increasing to decreasing. So you could see here where it hits the x-axis, it changes from increasing to decreasing, right? Hits the x-axis again, it changes from decreasing to increasing. So let's go ahead and do that. G prime of x equals to 0 means x squared plus 6x minus 1 equals to 0, right? We can solve for these. We can use the quadratic formula. X is equal to negative b, so negative 6, plus or minus square root of b squared, 6 squared minus 4ac, 1 times negative 1, all over 2a, 2 times 1. Right, that's just negative 6 plus or minus square root of 36 plus 4, 40 over 2. Right, let's use our calculator just to make this easier. So we have negative 6 plus square root of 40, right? And that is going to be 0.32455 divided by 20. Oops, divided by 2. Right, this is just a 2. So that's going to give me 0.162278, or if I now did negative 6 minus square root of 40 and then divide by 2, minus that, divide by 2, or negative 6.16228. Okay? So there, I'm able to see what things. I'm able to see that it's going to be changing from increasing to decreasing, it being g of x, right? G prime of x tells me where it's 0 here, that we're increasing from negative infinity until negative 6.16. Okay, so it's giving me this region. I'm decreasing then between negative 0.16 negative 6.16 to 0.16, right? Positive 0.16, this region. So I'm decreasing then in the region negative 6.16 to 0.16, okay? Sorry, it's a little bit messy here. Let me go ahead and block that off. Okay. Let me rewrite this 0.16. All right. Okay. All right. So then let's look at, so when we look at g prime of x, it's telling us now where we're going from increasing to decreasing to increasing, right? Now let's look at g double prime of x. So let's go ahead and graph that. This one is just a line with the y-intercept is 6. So it's going to be like this, and it's going to look similar. It's basically, whoa, it's hard to see. But it's just like this, right, with the slope of 2. Okay, so there's our line. Here, let me make it go longer. Okay, and where this point hits the x-axis is where we have an inflection point. Okay, so g prime double prime of x equals to 0 is where we have inflection point. We're changing from concave up to concave down. So let's go ahead and solve where this is equal to 0. 2x plus 6 equals to 0. 2x equals to negative 6. X is equal to negative 6 over 2, or negative 3. Okay, so now we know there is a point of inflection on g of x at x is equal to negative 3. Alright, so our point of inflection is going to be negative 3, comma, we can plug in negative 3 into our g of x to get the y value. So let's go ahead and do that. Right, we have 1/3 times negative 3 cubed plus 3 times negative 3 squared minus negative 3 plus 5. Okay? So let's go ahead and plug that in, and we get 26. Okay? So we have an inflection point at negative 3, comma 26. Does that match our graph? Yes, because this point, negative 3, comma 26, is around that blue point right there. Okay? So then let's go ahead and see, well, where's it concave down? Well, it's concave down to the left of that point. Or you can even say, where's g prime of x less than 0, right? So if we know g prime of x is equal to 0 at negative 3, at negative 4, and to the right of it at negative 2, negative 1, and so on, this is just a number line. So we know it's equal to 0 here, right? Now here, will it be positive or negative? And on this side, will it be positive or negative? We could go ahead and plug in a point like x is 4 into our equation. Or if we graphed it, we're going to see that it's concave down, right? So it's going to be negative here and positive here. So that means that it's concave down. Let me put away the calculator. Concave down now and concave up. So it's concave up to the right. So it's starting at negative 3 and to the right. So I can say negative 3 and to the right. Oops. And then concave down, starting at negative infinity to negative 3, right? So this allows us to get specific with all these points. All right. So let's go ahead and make sure we answered all these questions. So it's always helpful to relook at the question. Okay, so then we use the first and second derivatives to find the intervals where the function, the original function was increasing, decreasing, concave up, concave down, and where the points of inflection were. Okay, so I know it looks kind of messy, but we answered all the parts, both graphically and then algebraically using the first and second derivatives. Alright, so this ends CPM Calculus Chapter 3, number 149.